Hello again, everybody, and welcome to this If Oxford event. It's going to be a fun one tonight about exploring some extreme conditions. And we've got Andy and Shep from the UK Atomic Energy Authority to explore some of the materials that are needed to help nuclear fusion power work. So, passing on to you guys, let's find out about some super materials for extreme conditions.
Thank you so much, Dane, for that introduction. And welcome to this If Oxford presentation about super materials for the extreme conditions inside a fusion reactor. I'm Shep. I'm one of the coordinators at UK Atomic Energy Authority.
And I'm Andy. I'm experimental materials scientist here at UKAEA. So tonight we're going to show you inside some extreme materials inside our materials research facility, and we'll introduce the materials inside a fusion reactor, what a fusion reactor is made from, and we'll take a journey through the materials research facility and reveal how we can level up our materials. But first, we've got an interactive element to this presentation. If you grab your internet-enabled device and go to www.menti.com and enter the code, it's displayed on the screen, 7282025, it should take you to our first question, which is, what's the hottest thing you can think of? I've put Death Valley, California. That's the hottest place on Earth. I see we've got some other things going on in here. Collisions in the LHC. That's certainly very hot. Fire.
Big Bang.
That's pretty hot. Yeah. The Big Bang. Yeah. I have no idea how hot the Big Bang was.
It's like a cooked tomato. I like that one.
Yeah. I was thinking a microwaved mince pie. That's got to be the hottest thing, right? Yeah. I like inside a cooked tomato. That's very hot. Definitely. White dwarf. Yeah. We've got some excellent answers there. Thanks very much. We're going to have more answers as we go through the presentation. It's totally optional, but it's just a fun way of getting you guys to enjoy and come along and contribute to our presentation as well. So thanks for that. We'll have some more questions later on. And at the end of the presentation, you'll be able to enter your email address if you want a copy of all the responses. Great. Yeah. Freshly cooked pizza, plasma. That's great. We've got some excellent responses there. Thank you very much.
So we're just going to continue on here. We'd like to do fusion on Earth to generate electricity. Nuclear fusion is the process that powers the sun and requires immense pressures and over 15 million degrees centigrade temperatures. These conditions are required to fuse light atoms to make heavy ones, a process that releases energy. But Andy, in the core of the sun, if it's that hot, how can we possibly contain a fusion reaction on Earth without everything melting?
That's a great question. Actually, the fusion reaction inside the sun is quite slow, and that's a good thing because it means that the sun won't burn up too quickly. It'll actually last for billions of years. Instead, we need to actually increase the temperature so that we can get more energy out at a faster rate. We have to get all the way up to 150 million degrees. When gases are this hot, they turn into a plasma. And we can contain the plasma using a magnetic field. So we use magnets to contain our plasma. But we still need to put everything inside a box. And this is our box here at Culham at the UK Atomic Energy Authority, the Joint European Torus, or JET for short, hosted here at UKAEA on behalf of the Eurofusion Consortium. It's the largest working fusion reactor in the world, and we use magnets to contain the plasma. Now, while the reaction is contained by the magnets, the temperature of the reactor armor, the surface of the wall here, can reach over 1,000 degrees C. And if there are any plasma disruptions, a bit like solar flares on the sun, these don't just melt the surface of our reactor, but they can actually just vaporize it, just turn it straight into a gas and a plasma.
Whoa.
So, yeah.
Well, let's look at some of the components we have to deal with this heat. Here we see inside the Joint European Torus, or JET, superimposed on the left is a picture of real plasma inside the jet. And then on the right, it's all lit up for a photo shoot. You can see the walls aren't all smooth. There are a lot of different features to show. For example, those stripy things on the wall are actually radio frequency antennas, and they work a bit like a microwave oven to heat plasma. There's also ports, which allow us to see into the vessel during the experiment to monitor and measure the plasma. Now, let's take a closer look at 3 different important components which materials they can be made of. Here we have the first wall. This is exposed to high temperatures, so it needs to resist melting. It also needs to resist the erosion by the plasma. We call this sputter. One potential material to use here is high entropy alloys, or HEAs. Next is the blanket. This is like a cozy jacket that wraps all the way around the reactor and heats up as it absorbs neutrons. The blanket allows us to extract useful power from the reactor, and it is needed to be built from a strong, resilient material like steel. Perhaps the most challenging component is our diverter. This diverts helium byproduct from the reactor. The cooler edge of the plasma comes into direct contact with the diverter, so it has to handle huge heat loads, as we'll see next. Our leading candidate material for this is tungsten. This is a heavy atom, so it's not easily eroded by the plasma, and it doesn't absorb the fusion fuel, and it has the highest melting point of any metal. It also survives heat flux of over 10 megawatts per square meter. But Andy, just how much heat is that?
A great question. It's hard to visualize, but let's try. Imagine a 1 by 1 meter square on the floor. Now put an electric heater in the middle of it. These typically have a power output of about 1,000 watts or 1 kilowatt. Now on your meter square, you have 1 kilowatt. So you have 1 kilowatt per meter square. Now imagine placing 10 of those electric heaters in the same space. Now you've got 10 kilowatts per square meter. Now try and imagine putting 1,000 of those same electric heaters in the same space. Now you've got a lot of electric heaters, but only 1 megawatt per square meter. This is a lot of heat. It's similar to the inside of a combustion engine of a car. And that's at the lower end of our scale here. Next, if you imagine a space shuttle re-entering the Earth's atmosphere, the heat flux here is about 10 megawatts per square meter. Now, our combustion engine here is designed to survive for a long time, and we can manage that heat load quite well. The space shuttle only has to survive that re-entry for a few minutes, and the tiles can be replaced afterwards. Next, also space-related, we've got a rocket nozzle. These are usually cooled by the cryogenic fuel of our rocket, and they have to experience up to 50 megawatts per square meter in the combustion chamber. While these usually survive, they are an expensive and difficult component. Next, we have over 70 megawatts per square meter, and this is what happens when we do welding. This is a process which is designed to destroy. In our fusion reactor, our first wall has to experience this kind of heat load, about 1 to 5 megawatts per square meter. The diverter is in space shuttle re-entry territory between 10 and 20 megawatts per square meter. And those plasma disruptions I mentioned, those can be over 50 megawatts per square meter. So that's one of our extreme conditions we have to deal with, is heat and temperature. The next one is something a lot smaller. And for that, we're going to go back to Mentimeter. So go to menti.com and enter the code 7282025 if you haven't already. And we'll answer our next question, which is, what does the word neutron make you think of?
Oh, star, that's a good one.
Yeah, so neutron stars. Atoms, that's right. As we'll see in a minute, neutrons are part of atoms. Neutral, yeah. So unlike a proton, a neutron has no charge. No charge. Nucleus, yep, they are part of a nucleus. That's a slight spoiler for what we're about to see. I've written tiny because they are really, really small. Quarks, that's right. So neutrons are actually made of quarks. That's right. We've got some particle physicists in our webinar tonight, obviously. That's great. Thanks for your answers, everyone. Let's switch back to our presentation. So the atom actually has a structure. It's not just one thing. It's actually got things inside it, like electrons, which orbit around a nucleus. A helium atom is just 56 picometers across. That means there's 1 million of them across the diameter of a human hair. And the nucleus within is 1,000 times smaller. It also has a structure. It's made from protons and neutrons.
So the fusion reaction that we want to generate electricity also produces neutrons as a product. Here we can see an animation of a deuterium and tritium reaction. The two lighter elements are forced together in high temperature and pressures that cause a nuclear reaction, and which also releases helium, a neutron, and lots of energy. Assuming we could capture and perfectly convert all the energy into electricity, just 1 gram of fusion fuel could be enough to power 15 homes for a whole year. Even considering the limitations in conversion efficiency and some of the energy we need to keep the reaction going, this is still a huge amount of energy, and 10 times per gram that which we get from fission power. So it's good that the neutron carries some of the energy into the wall of the reactor, because this produces heat, which we then can use to generate electricity. However, there are some problems with these neutrons. Andy, what happens with the materials when exposed to a neutron?
So, as you said, when the neutrons deposit their energy in a material, they heat it up. There's also 2 other things that can happen. The first is transmutation, so the nuclear reaction, and the other is damage to the crystal. So, solids are made of crystals usually, unless they're a glass or another material we'll see later. When a neutron hits these atoms arranged in our materials, they dislodge them. And one atom that gets hit can get a lot of energy, and it can go on to hit another atom, and so on. And this is a bit like a snooker break. One atom can hit another, and it can create an entire cascade of damage. Here I have a computer simulation of one of those cascades. Here, an incident neutron hits an atom, and that atom knocks all of these other atoms out of place. The different colored dots you can see here correspond to the different types of defects which form. Now, there's a very similar process that you might be familiar with. If you bend a paperclip, you'll know it's easy to bend once and a bit harder to bend back. And if you keep going, eventually it will snap. Every time you bend that paperclip, you're introducing damage and defects. And as you keep bending the paperclip, that damage and those defects accumulate, and eventually they cause it to break. The same thing is happening here with our damage cascade. Normally, after the cascade, almost all of the atoms go back into a perfect lattice site, so that it leaves no problems behind. But some atoms don't quite go back in the right places, and others, there's just missing sites where there's no atom at all. So as we have these different damage cascades from all the different neutrons which are impacting our material, it accumulates damage. And that damage, just like in the paperclip example, makes our material harder and more brittle, and eventually it might break. Now, there's another negative consequence of neutron irradiation, and that is transmutation.
That's right. Transmutation is like alchemy, turning one element into another. This is bad for 2 reasons. One, you might start with one material, but after it's been irradiated, it now consists of a tiny quantity of something totally different. And this can cause big trouble. Secondly, the element created can be unstable, creating radioactivity. There are radioactive substances all around us, including inside of us. There's carbon-14, or even potassium in a banana you might have just eaten. Now, normally this is nothing to worry about, but there are certain times when you need to be a little bit more careful, like when having too many chest x-rays, or if you're an astronaut on the way to Mars. Luckily, for our materials, the elements created aren't random. We can model and predict the transmutations that will take place, as well as predict how long and how badly the material will become radioactive. This means we can choose a starting material which won't result in large quantities of long-lived radioactive waste. For contrast, in fission, where large atoms are split apart, the elements created are somewhat random, and the waste can be radioactive for hundreds of thousands of years. With fusion, we aim to recycle our used materials and have structural materials we can handle easily in about 100 years after we shut down a reactor. However, if we want to study real materials that have been neutron irradiated, it means we have to be protected from potential radiation. Now, if we were to research some radiated materials, you could go to a nuclear power plant or somewhere like, the Sellafield nuclear site. However, access is quite rightly very restrictive. And once you've got security clearance, the experiments you could perform on materials are limited. On the other end of the scale, the alternative would go to a university. Universities are right on the cutting edge of science and understanding materials. They have advanced equipment not available anywhere else. However, they are limited about the amount of radioactive material that they can handle. And this is why we have the Materials Research Facility, or the MRF for short. And this is why this was built.
So the MRF sits in between the nuclear license site level and the universities. We can handle moderately radioactive material, and we have some cutting edge equipment. Inside the Materials Research Facility, we have a line of steel boxes, which we call hot cells. We call them cells because it's a bit like a prison cell. Once something goes into a prison cell, it doesn't come out, and we don't want the radiation to come out. We call them hot cells because we informally refer to radioactive material as being hot, not because it's temperature or even spicy hot. We also have shielded research rooms. These have steel doors which can open, allowing human access inside to reconfigure the equipment or do experiments on non-radioactive material. But the shielded rooms also allow us to remotely operate on radioactive material. So here we have the compromise between what we can do and the amount of material we can handle. Before we take you inside the Materials Research Facility, let's introduce some of the materials we're going to be looking at. First of all, we've got tungsten, then we've got steel, and we've got our high entropy alloy. And we'd like you to vote on which material you'd like to choose to be. So I'm just going to switch to Menti and switch over to that. So you can think about voting right now, but we're going to explain each of these three different materials in detail, and then you can make your choice. So first up, we've got tungsten. As we said before, tungsten is, sorry, let me just see if I can, oh, why can I not hide my taskbar? Hold on a second. There we go. Okay. As we said before, tungsten is has the highest melting point of any metal. It's got high temperature strength and it's resistant to the plasma. It's not easily eroded by the plasma, which is great. However, the downside is that tungsten is a refractory metal. This means it's hard and brittle. This makes it difficult to machine. And it's also quite expensive. We already use tungsten in the diverter in JET, as shown in this picture down here.
Steel is an ideal candidate for a blanket structure. This has a huge mass, sometimes thousands of tons, so it has to be made from an abundant material. Iron is a low activation element, making a great choice for reduced waste. It has a limitation operating above about 600 degrees Celsius. And while it has some steels are more resistant to neutron damage than others, this is an area we could improve.
Lastly, for our first wall armor, shown in the picture here, we have the high entropy alloy. These have an engineered disorder in their atomic lattice. So there's that crystal structure in those atoms I was telling you about before. The disorder is where the term high entropy comes from. These weird alloys are made from lots of different elements, and they've shown an amazing resistance to radiation damage. But they're hard to produce and to join to difficult and to other materials, which might limit their future use in a fusion reactor. Okay, so let's have some fun. Head to menti.com and enter the code to vote. Let's switch and see what people have been voting on. Okay, we've got plenty of votes for tungsten there. We've got some high entropy alloys. No love for the steels though. Disappointing, that's my favorite.
Oh, wow, it's bouncing around quite a lot there.
We've got lots of people voting, that's great. Oh, it's almost neck and neck between tungsten and the high entropy alloy.
Oh, a little bit of steel, a little bit of
steel. That's great. Well, I think maybe that we've piqued people's interest with the high entropy alloys. They are very fashionable materials to study at the moment. Okay, let's assume that you're a high entropy alloy that's just been developed. You're a promising material, but you still hold some mysteries. Imagine you've been carefully prepared and exclusively neutron irradiated inside a fission reactor. Then you've been taken out, cooled off, and packaged up. Then you've been shipped all the way to the Materials Research Facility, the MRF, where you're going to be unpackaged.
So here's what's going to happen. You'll be unpacked remotely in the receipt cell. This has a sliding door to allow items in and out of the hot cell line. Then we're going to perform some simple checks to make sure that you've arrived in one piece. Then you'll be moved to the next cell where you'll get cleaned and polished and for more detailed analysis outside of the hot cell. But to get there, you'll have to be posted out through one of our hot cells into our shielded trolley. Then be moved into one of our dedicated shielded research rooms.
Great. Let's show you inside with our video tour.
Here we are arriving in the main hall of the MRF. In front of us, we can see the receipt cell. This is a shielded room where materials can be safely unpacked using a robot arm and a winch. We just need to shut the door first. We don't want any of that pesky radiation getting out.
That's right. These hot cells are designed to contain 3 terabecquerels of radiation. That's enough that it would kill you instantly if you were exposed to it. We have not had anything nearly that radioactive yet, but it's best to be prepared.
Now that you've been unpacked, you'll be ready to enter the first hot cell. Each of the cells is separated by lead shielded doors. These are to prevent radiation from shining from one cell to the next. Looking around here, you can see some of the equipment we can use to samples like yourself. But first, how do we move things around inside if we can't reach in?
Well, that's what those big white arms are for. They have grippers on one end inside the cell, and a human operator on the outside manipulating them. In this case, Darren, our hot cell operator, is going to be helping us. We call these remote manipulators, and the white plastic there is to prevent them from getting contaminated with radioactive material.
It looks like Darren's going to pick us up now. Here we go. First, he pulls out the transfer tray, and now he can show us around inside the inspection cell. Those bright lights on the manipulator are actually cameras. There's lots of cameras around inside the cell. This allows us to see in without letting any of the radiation out. Oh, Andy, what's that?
Those are just a set of scales like you might have in your kitchen. It's important to know exactly how much radioactive material you're dealing with. And to the right, you can see our mounting press. We often need to fix small bits of material into something larger to make it easier to handle and to take measurements from.
That's great to know. I guess the samples we're dealing with today can be seen to be moved around easily. We won't be needing our hot press, which is just to the right of that mounting press. This is like the mounting press. It can set a clear plastic around our materials. Instead, this holds it together and allows us to be moved around more easily. But Andy, what's that big silvery thing? Is that a gamma spectrometer?
It certainly is. Some of the radiation types emitting from our materials are gamma rays. These are high energy light emissions, similar to X-rays. And there's a clever trick we can use. By measuring the energy of the gamma rays emitted, we can actually tell what type of atom released it. So using this machine, we can tell which radioactive elements are present in the material and exactly how radioactive they are. The big silver shield is steel to protect the sensitive equipment from other radioactive material also being handled in the cell.
And to the right of the gamma spectrometer, we can see some of our optical microscopes. These let us get a real close-up view of a material. It's always helpful to see these things up close and check up if there's any scratches or damage on the surface. Now, here we're entering the preparation cell. Here in the middle, you can see some of the grinding and polishing machines. From the look of our sample, we'll just need to give you a quick polish and clean you up. Hold on. Andy, what's that yellow window there?
So this hot cell actually has a window into it, but it's not just normal glass. That's a 60 centimeter thick leaded glass window, solid glass. It's specifically designed to stop radiation. You can wave to Darren, our hot cell operator. Here you can see Darren operating the remote manipulators and handling material inside the hot cells. Thanks very much, Darren. There we go. All nice and clean and shiny again. On the front of the polisher, you can see that there's no controls or buttons. These have all been moved outside of the hot cell to make maintenance easier and make it simple to operate without having to press those small buttons with the remote manipulators. Above the polishing machines, you can see all the different polishing platters. These are how we get different grades of polish and different grades of grinding. Again, these have all been specially adapted to make them easy to use with the remote manipulators.
Now, here we can see a diamond saw cutting up a large piece of material. By cutting things up, we can make them smaller, but this also means there's less radioactive materials to deal with. Now we're going to be transferred into a cell that has an opening so we can post out small samples from the hot cell into the shielded trolley, and so we can be moved around the MRF. The trolley can be taken into one of the shielded research rooms. Oh, and here we go.
And here we see the shielded trolley being moved into one of those research rooms so that we can perform some more detailed analysis. So thanks very much for watching that tour. We hope you enjoyed it. If we head to Mentimeter again, we can ask, what did you find surprising or interesting about the tour? I think my favorite thing was actually seeing inside the tunnels between the different hot cells. Until the hot cells had been constructed and put together, ever since then, I've never seen inside the hot cell since they've been closed up. So I thought that was really interesting. Shep, was there something that you enjoyed?
I really enjoyed watching Darren using the remote manipulators. I thought that was really cool. Yeah, I see somebody else enjoyed that too.
Yeah.
I think also, Andy, your camera has actually stopped working there if you want to try and give it a kick.
I might just turn it off.
Oh, yeah, the diamond saw I think was really cool. I'm just looking at some of the answers coming in here now.
Yeah, we've also got a diamond wire saw that we didn't show you, which is very useful. Okay, I'm going to switch away now. I'm just going to turn my video off. There we go. Sorry about that, everyone. So you can keep typing in your responses there while we go on to the next part of the talk, where we learn about some of the different scientific equipment that we use. Inside the research room, when the door is closed, we can use a robot arm to take the sample out of that shielded trolley and remotely load it into the scientific equipment. Obviously, we can't be in the room when the sample is out of the shielding containment. The robot arm can also shut the door, and then we can use this equipment here, in this case it's a scanning electron microscope, to perform experiments on our material. Inside the electron microscope, we have a beam of electrons which shines onto our specimen, which is in the middle here. This creates different signals, which we can use different detectors in the microscope to detect, and then to make measurements. Of course, we can't operate the equipment from the room. We have to do that from the control room. This is a separate part of the building, totally shielded from the main hall. So we can operate all of our scientific equipment remotely from the control room. And here I am, sat in front of the scanning electron microscope controls, ready to perform some experiments on this high entropy alloy that we've been given. As we shine electrons on our specimen here, it casts an interesting pattern on the detector. This geometric pattern actually reflects the arrangement of the atoms in our specimen. As we move the beam across the sample, we can build up a picture of these different arrangements, and we could use a computer to index those patterns. It tells us what orientation the crystal is at these different positions. And this gives us a two-dimensional map of our materials. These different patches, which are different colors, they're colored by the different orientation of the material. And these we call grains, kind of like grains of sand. These grains can actually tell us a lot about the properties of our material. It looks here, by looking at my notes, that after the irradiation of this particular high entropy alloy, the grain size has increased. Now, this is something that happens when we thermally treat specimens. So if we heat things up, the grains tend to grow, a bit like if you leave the bubbles on the surface of your washing up, they slowly get bigger over time. Irradiation is also known to help accelerate this effect. That's very interesting, and it might have some negative consequences for our material.
So this might seem like a lot of effort to go to, for a small bit of metal. However, irradiating materials gives us experience. Seeing how these materials behave in a challenging environment, allowing us to level up our understanding. We can use this knowledge to improve them further. Let's look at our 3 example materials. For tungsten, we want to make it less brittle. If you think about a copper wire in a cable, you know that there's a lot of bendy big pieces of metal, and this is a lot easier to bend than a big piece of copper. If we take tungsten into a wire and make it more bendy, if we stack a lot of tungsten wire together and fill the gaps with more tungsten, we can create a fiber tungsten composite, as shown in the image on the right here. This helps stop cracks and prevent failure.
For the steel, we can make it stronger at high temperature by introducing tiny oxide particles. These particles are only a few nanometers across. The scale bar in this image is 100 nanometers. That's the same size as a coronavirus. And you can see these little white dots, those are our tiny oxide particles. These help the material become even stronger at high temperature, and they help trap and eliminate some of the defects which are caused by irradiation.
Now, for the high entropy alloy, or the HEA, we can tweak the composition. We know that some of these alloys can break down when irradiated. If we change the composition, perhaps we can avoid this. Maybe tweaking the composition, this makes it easier to produce or bond with other materials while still maintaining amazing irradiation resistance.
So what does this mean for our future fusion power? Well, we've established a route for scientists and industry to investigate materials like never before, enabling understanding areas that we had only once touched on before. Improving our materials means our fusion reactors can last for longer. This means less materials cost and less waste to deal with. In some cases, we might not be even able to use certain components unless we can improve our materials beyond a certain point. This is where we stand now, on the edge of fusion power as a reality, but it needs materials, and those materials need to be developed and understood now. Otherwise, how can we design and build a reactor out of them? It's an exciting time to be a material scientist and to be part of the UK's fusion future. Thank you very much for listening.
Thanks for listening. And don't forget to check out our Engineering Stars event on the 28th. And we hope you enjoy the rest of IF Oxford. We'd love to take some questions. I see someone coming in through in the Q&A function now on Zoom.
And it was a really interesting presentation. Thanks so much. I have a couple of questions. Of course I do. And there are some questions from people who are also really obviously interested in what you've spoken about. So there was a question about how do you radiate the samples in JET, which is the Joint European Torus or the fusion reactor?
That's a good question. I'm happy to answer that. So we have some specimens, we kind of have like a little canister on the side, and we've got a bunch of little things attached in there. Most of the materials that we irradiate, though, we actually have irradiated in normal fission reactors. So there's over 200 research reactors around the world, and these are doing normal fission, so taking uranium and splitting it. This produces neutrons. So they're not the same energy neutrons that we expect in a fusion reactor. So we have to be a little bit careful. But we can use that to get a really good understanding of how the irradiation is damaging our materials. So mostly we use materials that have come out from fission reactors. Okay, it's a good question.
There was also another question about the polishing part. So why do the samples need to be polished before they're looked at? Is there a difference if they're rough?
So often ideally what we'd like to do is kind of get a look inside a material. And if you've got something on the outside, sometimes the outside is really interesting. So if you've got material and it's been exposed to water or steam or something like that at high temperature, then you can basically form like rust on the surface. And we don't want to clean that off. We want to know about that, and we want to know how much our materials corrode, especially if they're being irradiated at the same time that they're in this corrosive environment. Often the surface is not important to us. So it's just, how it was prepared previously, or maybe it's scratched or damaged. And so what we want to do is very carefully clean away the outer surface to get to the kind of interesting interior of our material. And then these surface sensitive techniques like scanning electron microscopy, or if we're taking small samples from the surface, we want a pristine surface to start from. So that's why we need to be able to grind and polish in the hot cells.
Scanning electron microscopy, could you just say what that is? I mean, I'm aware of,
yeah,
people might be familiar with the kind of microscopes that you look at through these little kind of put your eyes through them. What is an SEM? And there's also another question about TEM, which is transmission electron microscopy, I think.
Yeah. Maybe the best thing would be, I'll just switch back to my slides with the picture of the inside of the SEM on it. If I can figure out how to do that again. Where are we? Screen. So this is inside the scanning electron microscope. So this big silver cone here, that's where our beam of electrons comes from. So we have an electron gun at the top. And this, we extract electrons from that. They're accelerated down, and we get this beam of electrons that hits the sample. So the analogy in a light microscope that you might have used is that this is like the light shining on our sample. So we're shining electrons on the sample. And then when those electrons hit something, then they usually do stuff. So they can produce X-rays, they can be scattered. We can detect the electrons which are coming off and what direction they're coming from. And it works if you're just using it in a kind of normal mode. You scan the electron beam over the sample. So you're sort of like the pixels on a screen. You get a reading at each of those different points. And as you make lots of readings in a sort of square map, then you can actually form an image. And we can do this with a much, much higher magnification than you could with an optical microscope. So with a light microscope, the limitation is about a micrometer. So that's it's good enough to see cells, biological cells, but not viruses, for example. Whereas with a scanning electron microscope, you can have much better resolution, so maybe about 100 times better. And the question about it's called scanning because it scans across the surface. It's called electron because it uses electrons, and it's a microscope because we're looking at things that are small. That's what microscope means. A transmission electron microscope actually works very similar. So you have this beam of electrons, and they hit a sample, and rather than looking at what bounces off or what's reflected, we actually look at what goes through. So this is a lot like a transmission optical microscope in biology, where you have a thin sample in the middle and you shine light usually from underneath, and then you look at it with an eyepiece from on top. Electron microscopes, for whatever reason, are usually the other way up. So you have an electron beam at the top, you have a very thin specimen in the middle, and then you have some kind of camera or the detector below the sample, which is detecting the electrons that have gone through it. Sorry, that's a very detailed answer. I hope that's appreciated.
Okay, so what you're effectively doing is you need to polish something down to make it nice and flat and see what's inside. Yep. And then you're either looking at it from one surface or you're almost holding it up to the light and seeing what's inside, so by seeing through it using the transmission electron microscopy.
Yeah. Yeah, we've got a whole bunch of other equipment. For example, one of the pieces of equipment I use a lot is the Nano Indenter, and this is quite crude. It's just a little bit like hitting your specimen with a very small hammer, except we're measuring all of the force and the distance that it goes in every time. And the idea is if you press a sharp tip into the surface of something and it's very easy to deform, then your material is soft. And if you press it into the surface and it doesn't really deform, then it's hard. And that is actually a very useful technique, because it's actually telling us about the kind of mechanical properties, which is interesting from an engineering perspective. We need to know, how strong our materials are. But we can do this on a very, very small scale. So again, down at the micrometer level. So that's kind of, you could maybe even think about testing an individual red blood cell. I mean, I've never done that. I don't know if everyone has tried, but that would technically be possible with this equipment. It's very sensitive.
So a microscopic version of poking your finger into some soft clay, or trying to poke your finger into a plate.
Yeah, exactly.
You might have your dinner off that's very, very hard.
Yeah, but much more expensive.
Much more expensive, much more sciencey.
Yeah, exactly. Yeah.
So moving on from the kind of soft clay and the kind of dinner plate idea, I think there was a question about, do you ever use ceramics? And I think Shep was going to answer that one.
Yeah, so I believe when Jet was first started, we actually did use ceramics in parts of the wall, and it wasn't found to be very good. We moved on to things like graphite, so like the graphite you'd have in a pencil. Obviously much bigger, not, a millimeter across or whatever. It's finding all those different the different irradiations and stuff like that go into the wall, and how it all works together. And ceramic, though fantastic for heat, isn't very good with things like irradiation and stuff like that. So we've moved on now, and we're currently using tungsten in the walls. So yeah, we have used it before. Just it's not great for the current implementation of JET.
Okay, thank you. There were a couple of questions about materials being damaged. So one of them is about when you're looking at the materials, does that then damage them? So does the electron microscope cause the materials to change a little bit? And then there's another question about irradiation of the materials, for instance, steel, or maybe even the HEAs that you talked about. How do the materials change their properties over time? And if you're looking at them, do they change even more?
Mm-hmm. That's a great question. So you've obviously got some very insightful listeners today, or viewers, I guess. So looking at materials, does it change them? It can do. So the thing about electrons is that they're very small. So they're about 1,000 times smaller than or lighter than a proton. So if you have something like steel, that's then like 50 odd thousand times heavier than an electron. Now the electrons might be going very fast. So there is a point where if your electrons are going fast enough, then they can start causing the same or similar sort of displacement damage in our material. They can knock the atoms out of the way. In a scanning electron microscope, that's not really a problem. The energy of the electron beam is usually a lot lower. In a transmission electron microscope, then yes, that is potentially an issue. So there are microscopes specifically at lower accelerating voltages, which has challenges in terms of optics and things and getting good resolution, but they cause less damage. And that's really important for biological specimens, actually. So using, or if you've got graphene or something like that, you need to use a lower accelerating voltage. In Japan, for example, they've actually used very high energy electrons to cause damage in a material. And there you have this thing where, yes, you're damaging the material as you look at it, but you're also seeing the damage you're creating as it's happening. And there's a tremendous value in able to be, seeing things as they happen. And so using an electron microscope to actually damage your material is kind of a beneficial thing, because then you can see the damage and you can see it change. In terms of the properties and what can happen, there's a whole big raft of things that can happen. So the first thing, you've got these displacement cascades. These create these small defects. Those small defects can then kind of clump together and form clusters. So we get a bunch of extra atoms sitting in a material. We also get vacant sites, so bits where all of those extra atoms had to come from somewhere, so they left a hole behind, and those holes can actually join together. And if you get enough of those holes together, we call it a vacancy or a void. There's just like a hole in your crystal. Now you've got like just a bit where it's missing. There's nothing there anymore. If you've got some of this transmutation happening, you can create gases like helium and hydrogen, and they can fill those holes, and then you actually get bubbles. So your metal actually kind of turns into a foam. It's got all these bubbles in it, and that's really, really bad from a mechanical properties point of view. It makes things very brittle. Like your really lovely steel you started with can turn into a glass if this, it just snaps, which is awful. So we've got to find a way around that. The other things that can happen, it rearranges the chemistry of your material. So we've done all our nice heat treatments, we've picked our composition really well, and then you put it in the reactor and it gets irradiated and everything moves around. Your nice heat treatment is destroyed and you lose all of that kind of materials engineering. And that's why we want to use these oxide particles in the steel, for example, because they're really, really resistant. I guess they're ceramics, these little ceramic particles. It doesn't want to be in the metal at all. It wants to be together in its own little, particles. And so they're not easily damaged, and they're very, very resilient. And so that's really good for keeping everything together. There's some other nasty things that can happen. Like we said, sputtering is like a surface effect where you literally knock atoms away and they're not there anymore. That can be pretty bad. And irradiation just tends to make everything worse. So, if you've got corrosion, normally it makes corrosion worse. If you've got cracks or something, normally it makes that worse as well. So it's generally pretty nasty environment to have to operate in.
It sounds pretty intense, actually. So I was really interested in these HEAs, the sort of highly entropic alloys. Mm-hmm. Is that right? Yeah. There's a question about what makes them so quirky. You've been talking quite a lot about materials, and there's not enough time to go on what's the difference in the glass, the ceramic, and alloy, and metamaterial. But there is a question about HEAs. What makes them quirky?
So when you have a normal metal, then it conducts electricity. And if you look at the arrangement of the atoms, they're normally kind of regular and periodic. And you have this kind of structure, this order that extends over long distances within your material. So on the scale of those grains that I was showing before. In a high entropy alloy, these are normally made up of at least 5 different elements or more, sometimes more, and in more or less equal components, so equal compositions. So you take an equal amount of 5 or more different things and you mix them together. And this is what people have been doing for the last sort of 15 years. There's been lots of this. And when you do that, if you melt it and then cast it, then you tend to just get one homogeneous material. Well, sometimes you do, but you usually don't get these different phases and you don't get things happening. You just get this single flat material. Everything, all the atoms are just kind of all jumbled up. It's not like a glass, which is just totally random and amorphous. A glass is a little bit like a solidified liquid. Like it's just all the atoms are jumbled up and then they freeze. In a glass, that's the same. In a high entropy alloy, we still have a crystal structure, but there's no long range order. So it might go, rather than going A, B, C, A, B, C, A, B, C, now it goes like A, D, F, A, G, A, B, C, whatever. So it's just random. So by doing that, you actually change a whole bunch of kind of fundamental ways that the crystal behaves. So when you squash them, they don't behave like normal metals when you squash them. When we irradiate them, the atoms kind of move around sort of more sluggish. So we're actually stopping that clustering, which is bad for our materials properties. There's really interesting. There's also a lot of high entropy alloys which are just terrible. There's a lot of people in computer modeling who are trying to figure out what makes a good high entropy alloy and what makes a bad high entropy alloy. That would be really,
all alloys are
really
very
super.
different, and some of them might have really interesting, useful properties, but some of them might just be, as you're saying, just a bit rubbish at the things that you want them to do. So I think there is a question, we're over time, but we're just going to kind of wrap up with a couple of these questions. There was a quick question about what happens to the waste when you polish a material. I think Shep is going to answer this one.
Yeah, so this is actually it's quite funny in how simple we deal with the waste sometimes. So it depends on if we're talking about the waste that's generated from the air or generated from the process. So like we just use air filters coming out, just like as if you're using your face mask now, the air is filtered as it comes out, and we try to use as tight a material on the filters as possible to get that out. If it's water waste, we actually have big water tanks that we hold, and then we filter out the water. And then we're able to then, am I right in saying then the actual materials themselves, when we're finished with them, they're then dealt with as if they're a nuclear waste. As if it's from a fission reactor or whatnot. So kind of fairly simple. We either wash it, clean it, or throw it out into a very specific dump. Yeah.
And we use whatever processes are necessary to produce as little waste as possible.
Yes.
So mostly we're using processes that use a very small quantity of water or no water to minimize the amount of waste which is produced there. Yeah.
Okay, well, there's one final question that I'm just going to ask. I think it should be quite quick. There's a question about the 3 different materials that we've talked about: tungsten, steel, and the HEAs. By and large, what's the half-life of these materials once they've been inside jet of the radioactivity?
Yeah, so the complicated thing there is that even a single element usually has multiple isotopes, and it's the isotopes which is important. So isotopes is when you've got the same number of protons but different number of neutrons in an element, and it's the isotopes which are important. So some isotopes, you can irradiate them with neutrons, and they might be very active for a very short period of time, even like 5 minutes or something, and then they decay into something stable. And other isotopes are radioactive for a much longer time. Now, jet is basically not really a problem. The main issue with jet is that we use tritium, and tritium has a half-life of about 12.5 years. For the most part, we can just heat materials up, and that means they release the tritium. In terms of activation problem, is not really an issue because we don't actually produce that many neutrons in jet, which I guess is a little bit embarrassing. Jet was never intended to do what we're doing with it now. It was never designed to really generate real fusion power although the people who designed it, they had a dream that maybe one day it could be used for that. No one thought that we'd be doing with it what we're doing. Next year, for example, we're going to do some really exciting experiments. So watch the news next year for our new deuterium tritium campaign. But,
sounds exciting.
Yeah, bottom line, not very many neutrons, so radioactivity not really a problem. If we irradiate things in the demonstration reactor, so this is the sort of next generation reactor which we want to build. So EU has an EU demo. They have a timeline for when they want to build that. After, I think it's 1 year in demo, you're looking on the order of somewhere between 40 to 60 years for those 3 different materials before they're hands-on waste. So, material you could just pick up with your hand without worrying about how radioactive it was. So tungsten and iron, for example, are pretty safe. Again, we know what materials are going in. We know how radioactive they're going to become. This is pretty well known and something that we can validate quite easily.
So compared with some of the half-lives that we might have heard about for fission reactors, quite short.
Yeah. So there's we obviously we want to be careful with the amount of waste that we're producing, and we don't want to produce long-lived radioactive waste because that's a nightmare for everybody. Yeah. So yeah, exactly.
And also one of the great things about fusion is we actually generate most of our own fuel from the actual reaction itself, as whereas fission is destroying its own fuel as it goes through. So it's technically a renewable source. Yeah. It's all a renewable source.
Yeah. Well, we're using hydrogen, which is the most abundant element in the entire universe. So I don't think we have to worry there.
That's good news, isn't it?
And anyway, on that, I think I'm going to go. So thank you, everyone, for listening.
We're over time. Thanks very much, everyone, for so many interesting questions. Thanks for providing equally interesting answers. Enjoy the rest of your Sunday evening. Good night.